Okay, so we're in business. Last time we were talking about Green's theorem. Well, we almost got to Green's theorem, but not quite. So let me review what we did. Reminder, just sort of big overview picture. I'm going to have to develop certain, what I'm going to call sophisticated ideas, just so that we can kind of piece them together. And once we piece them together, that's going to give us a powerful computational tool. Unavoidably, though, this powerful computational tool is made up out of these sophisticated kind of ideas. Okay, first, we talked about the word boundary, right? And previously we thought of boundary as just meaning sort of the dividing line between where the set is and where the set isn't. Now, going forward, and for the rest of Chapter 6, for the rest of Chapter 7, this word boundary is oriented, right? So boundary does not just mean a curve in this case. Boundary means an oriented curve, and specifically oriented in a very specific way according to a very precise rule. And the details of that, sets on your left, blah, blah, we talked about a lot last time. I'm not going to repeat all that. But the big point is we talked about what we mean by the orientation of a boundary and how this is now a loaded word going forward. Okay, that was the first one. Next, we talked about this idea of accumulation. And again, not really a new idea. It's just new to talk about it. Because in fact, every integral we have ever done in this class was a way of representing an accumulating quantity. Right? So the whole reason that we can write mass as an integral is because the whole is the sum of the parts. When you're talking about mass, if you have a certain amount of mass and you chop it in half, well, the original mass is the sum of the two individual pieces of mass. That's just how mass works. It's unavoidably an accumulating quantity. Ditto every example we've ever solved with an integral. We have an accumulating quantity, and we are literally chopping it up and adding up. The whole is the sum of the parts. Again, different ways to say it. So why are we talking about this feature now if, in fact, it's obvious and been in every previous example we've ever seen? And the reason is because, for one thing, not everything is, and furthermore, the thing that we're going to be applying it to is really not obviously an accumulating quantity. In fact, it looks like it isn't. It's not only not intuitive, it's counterintuitive. When I say boundary circulation accumulates, it's pretty tempting to say, come on, no way, couldn't possibly. Look, when you cut the piece into two, we get new perimeter. That's going to create new terms of line integral. Surely that's got to matter. So I had to dispel this counterintuitive idea that wouldn't make a difference. And of course, the point here is that on this shared edge, yes, there are two new terms in the summation of line integrals, but they have opposite orientations, with one oriented that way and one oriented this way, and they cancel in the summation. Okay, so boundary circulation. This is going to be the object of interest. This is the thing we're going to be accumulating. This is going to be the kind of like mass, kind of like, population. This is going to be the thing we're chopping it up into pieces and adding up over our area. So I needed to establish the very non-intuitive fact that it is indeed an accumulating quantity. Okay, and then there's this whole business here, and this is surprising. When we talk about boundary circulation, or vector line integral along a curve, it's tempting to think of it on the curve. After all, that's where you compute it, right? And I'm proposing this counterintuitive idea here that we should not think of it as being on the curve. After all, it's when I cut the solid region in half that we get the accumulation feature, right? So I want to think of boundary circulation not as a property of the perimeter. I'm not chopping the perimeter in half. I'm not chopping up the perimeter into little pieces. It's not what we're doing, right? Very importantly, we are chopping up the area chopping up the area into little pieces. So I want to think of boundary circulation because it is accumulating over the area. I want to think of it as actually being on the area, that it is a property of the area. Think of it as a kind of a stuff that is distributed over the area. And again, counterintuitive. It's going to seem weird to do that, but it behaves algebraically as if it is, and so it's constructive, edifying to think of it as if it is. Okay. All right, so that's where we left it last time, and we're going to move on now. This idea of density. Now, we've talked about density before. Of course, everybody sees density in ninth grade. Well, okay, they changed the way the courses work in high schools every couple of years, so who knows when y'all first saw it. But I saw it first in ninth grade, what they called physical science class. And they were very rigid about what density was. Density meant mass specifically, per unit volume specifically. It was very narrow-minded in what the word density means. So, reminder, we've generalized that to mean stuff per unit size, stuff of whatever sort, as long as it's an accumulating quantity. Right? Any accumulating quantity, such as mass, nice, convenient, physically satisfying example, but not necessarily per unit volume. So, for example, if you have mass distributed over a two-dimensional region, right, then we think of that as mass per unit area. Area just happens to be the appropriate notion of size here, right? So we call this specifically mass, I circled the wrong thing. We call it mass density because mass is the quantity. Mass is the accumulating quantity. It's the numerator in this, writ large concept of density that we're describing here. Okay. All right, so by that analogy, again, you can talk about density for any sort of an accumulating quantity. For example, we've talked about population density. It's a different quantity. It's not mass, right? When we say population density, we mean count, number of people. It's a different kind of a quantity. But it's an accumulating quantity, and so we can talk about a density associated to it. And so we talk about population density, old concept. And, well, going along with what we saw on the previous page, circulation is now an accumulating quantity. Boundary circulation, to be more precise. But so with that in mind, with boundary circulation as our numerator, this is the quantity that we're thinking of as, distributed over the interior. And I can talk about how much of that boundary circulation is there. Here's a representation of boundary circulation. Again, I think of it, though, as being in the interior. Boundary circulation per unit area. This is what we mean by circulation density. And it's a trippy idea to try to absorb in your mind because we're accustomed to thinking of densities as being stuff per unit size, mass, population, whatever stuff you're interested in keeping track of. Just remember, boundary circulation now is kind of a stuff. It certainly behaves like a stuff. It's an accumulating quantity like stuff. So, seems weird, but perfectly reasonable to talk about it as an accumulating quantity and therefore to talk about its associated density. All right, y'all on board? Willing to play along with that? Okay. All right, so let's talk about circulation density. What is it? How do I compute it? What notations are we going to use to represent it? And this is there's a lot of things to say here. Circulation density. Here's the formula. If you have assuming you have a vector field P comma Q, here is our formula for how to compute circulation density. It's dq dx minus dp dy. That's just that's what it is. Now we could prove that. And proof's in the book. If you want to see it, go ahead. It is arguably a very important calculation, but it is also a bunch of details, and there's so many what I consider to be more important concepts going on here. I don't think this quite makes the cut for something that I want to focus on in this course. So I'm just going to state this as a given. Again, if you're interested in the details, it's in the book. You're also very welcome always to come to my office hours and ask me. I'll be very happy to walk you through this argument of why this is the circulation density formula. But for the purposes of this class, we're just going to take this as a given. Now let's talk notation and terminology. We are seconds away from being able to write down this thing called Green's theorem, in which there is an operator, namely this thing. And so because this is the primary player, the primary operator involved in Green's theorem, I think it makes sense to call it Green's operator. So you're going to hear me talking about Green's operator, by which I mean this, by which I mean circulation density. Okay. Notations. I think it's pretty natural to motivate this little abbreviation GRN as an abbreviation for green. I think that makes sense. I like to use this notation. It's just a notation, not important. But anyway, when you see me write GRN, I mean Green's operator, aka these other things that I have circled in purple. Here's another one, and I actually like this one pretty well too. ROT, R-O-T. It's an abbreviation for rotation. And remember, when you talk about circulation is a representation of, to what extent is the fluid kind of doing like that? In other words, to what extent is the fluid kind of going in circles, which we related to what extent, if I put a little leaf down on the surface of the river, to what extent is that leaf going to be rotating? Right? So I think this is also a very reasonable notation. Rot F represents how much little leaves in that fluid will be rotating. Very natural. So dig it. Feel free to use that. I like it very much. Perfectly fine. And now we get to a couple of notations that I don't really much care for, to be totally honest. So this one here, let's see, I'm going to do this in red. Warning sign. Curl. Very common choice to call this curl. What I don't like about it is that there is another concept called curl. You may remember from chapter 3. It's a three-dimensional concept. And here's the justification. just to play devil's advocate for a second. This curl is a way of measuring the extent to which the fluid is kind of rotating. The three-dimensional curl we will talk about is also, in its way, a way of measuring to what extent the fluid is kind of rotating. So they have a lot in common. This is not an unreasonable notation. My problem with it is that this thing is a scalar. Formula right here, this is clearly a scalar, right? Curl, as it's been defined in 3 dimensions, is not a scalar, it's a vector. And so this thing being significantly different, it's not just different, it's a different kind of critter. It's a fundamentally different object. I'm uncomfortable using the same name to represent 2 fundamentally different things. So, I'm not, look, I get it. I know this is very common, but when there's so many other alternatives, I just don't see why would we want to call it a curl. It seems to create confusion to me. Then this one here. This one, I'm going to go so far as to say it's just awkward, and I really don't like this notation. Now, our book uses this notation more than once. Here's my big gripe with it. Now, I'm all in favor of the idea of symbolic notations, determinant, the way we've written determinant, right? The way we've written cross products, the way we've written curl, in fact, in the first place. It's all kind of symbolic. The real problem here, though, is that this vector, P comma Q, only has 2 coordinates. So what do you mean cross? even from just a symbolic point of view, I think this is a disconnect and problematic, right? Now, there is a point of view on this as well, and yes, I understand what that point of view is, and frankly, I'm just not very persuaded. I just think this is too awkward. Again, it's just notation, and arguably, okay, I guess you can use whatever notation you want when you write a book, and Kali has. I still don't like it, and I ask that you just don't use this one. I don't think it makes any sense. I don't think there's any reason. I don't think there's anything about this notation that makes it more desirable. I think it's all downside. So FYI, yes, it is in the book. This is what she meant when she put this in the book. I'm going to mark this as just not a good notation. Okay, everybody good with the notations and terminology? Keep in mind, all of this, what we're talking about, is circulation density. All right. We have all of our pieces. We are ready to assemble the theorem. We kind of already have a Green's theorem. We just don't even realize it yet. And here it is. Here's how it comes together. We talked about circulation as being a kind of a stuff, as being kind of a quantity, kind of like mass in a way, that I can think of it as sort of vaguely pseudo-physical, even though it isn't, fine. But we can think of it that way. It behaves that way, so we can think of it that way. Okay, don't forget we have this notation, sigma, lowercase Greek letter sigma, to represent circulation. Next observation we made. Well, another observation we made. It's an accumulating quantity. The whole is the sum of the parts. And that's all that's happening in this equation. When I say circulation, double integral d sigma, I just mean that I'm going to chop up my domain into a bunch of areas, a bunch of little sub-areas, and on each one I'll compute a circulation, and I'll add up over all the pieces. That's all that means. The whole is the sum of the parts. Okay, and with that done, we have this idea of density up here, and I guess I have to zoom out so this will fit in. We have this formula up here that tells me what d sigma is. It's circulation per unit area times area. It's circulation density times area. Which I put there. And I'm using for circulation density, you'll see I'm using this notation here, Green's operator, Green F. So, putting those pieces together as I have, notice all together, that gives us a theorem. That tells us that if you have a line integral over a boundary curve, specifically a vector line integral over that boundary curve, boundaries being closed, that means we have a circulation over a boundary. In other words, if you're looking at a boundary circulation being our accumulating quantity in question, chop it up, add it up, and the punchline is you get a double integral of Green's operator over the interior. This is Green's theorem. It's just the way we write down what I like to streamline, summarize as we're chopping and adding boundary circulations. This is just the accumulation of boundary circulations. Everybody with me? Okay. Now, computationally, why do we care about this? Well, computationally, what this means is if I find myself looking at a line integral, I don't have to compute that line integral, boundary line integral that is, I don't have to compute it as a line integral. I can say, you know what, for whatever reason I don't like that, I am instead going to compute this corresponding double integral. And sometimes that double integral is a lot easier to compute for whatever reason. So very powerful that it turns one kind of integral into a completely different kind of integral. And, again, sometimes that's a win. So that's all it is. Green's theorem. Let's see some examples. All right. Now, first thing I want to say about this first example Notice in the statement of the question, vector field given, curve given, orientation and everything. We've been asked here, compute this vector line integral. Notice nowhere in the statement of the question does it say circulation. So, in some sense, this is a sneak example, right? The way we're going to approach this example is by recognizing that this relates to a circulation, but it didn't tell us to do that. We have to recognize that. So how do I know that this is the direction I should be going? How do I know to think in terms of Green's theorem here? Well, my domain, it says right here, is the unit circle. A circle is a boundary. Now I'm going to commit some math crimes here. Forgive me, I'll do my penance in a second. But says right here that if you are doing a boundary line integral, you can rewrite it as a double integral. Seems like we're in business. Okay, so notice though it's on the recipient of the question. The askee, not the asker, right? To recognize, oh, hey, check it out. That's a boundary. This is not just a random curve off the street, right? This is specifically a boundary curve. And so Green's theorem's on the table. The askee has to make that realization. Is everybody on board? Everybody see how that? Okay. All right. Okay, now let me confess to my crime. In fact, this is not a boundary. Right? It says right here, it says clockwise. Boundaries can't be clockwise like that. Right? If I look at the, you know what, let me make a different color choice here. Let me look at, here we go, clockwise oriented unit circle. The region's on my right, not on my left. That breaks the rule. This is not a boundary. Everybody see? But, I mean, except for the orientation, it's a boundary, so I feel like if we're within shooting distance, we should still be able to use Green's theorem, but I do have to recognize, as stated, this curve, not a boundary. So, easily fixed. All I do is I just say, okay, well, let's look at the curve going the other direction. That's the exact same curve. The only difference is the orientation is backwards. This curve is a boundary. No problem. It's literally the boundary of that disk right there. Right? And being as it is a boundary, we can use Green's theorem. So that green curve is what we want to talk about. That green curve is susceptible to Green's theorem. But now I got to recognize, though, that I am there is a price to be paid here. So the blue curve that I'm given, and the green curve that I want to relate it to, they do have the opposite orientation. And when you have opposite orientations, you get a minus sign. So step one, I want to acknowledge, and you notice in the very first step that I took over there, very first thing I do is I recognize that when I switch the orientation on my curve, for self-interested reasons, I pay the price by putting in that extra minus sign. Yeah? Everybody all right? Okay. Next. We recognize, as is already noted, right there, that C minus is a boundary. Specifically, it's the boundary of that yellow region. That's important. The fact that it is a boundary is what allows me to do the next step. The next step is where I apply Green's theorem, in which I recognize that this, very importantly now, boundary circulation can be computed as a double integral of Green's operator over the interior. The interior, of course, being that yellow disk. Oh, and let's go ahead and color in. So the boundary is the green curve. The interior is the yellow disk. How are we doing? Is everybody on board? Okay. Now, there's a lot that happened in this first line. Big ideas afoot, right? And do keep in mind, I think it's really important for me to emphasize these things as we go along. This is a course about ideas. It's a course about reasoning. And when you're explaining your understanding of deep ideas that go into a calculation, you need to give me a recognition, doff the cap to the big ideas in play. So, in particular, and I wrote this example with this in mind. Notice this is in recognition that the orientation is the wrong way from being a boundary. This step is in recognition that the thing that I switch to is, in fact, a boundary. And this is where I apply Green's theorem. All of those are big, substantial ideas. And so I think it's everybody wins, right? If you, in fact, show all three of those steps, because they're all significant concepts. Now, by contrast, some students will just, very first thing they write down is this. And I say this is really, there's a clarity problem here. The line integral around the given curve is the negative of the double integral over d of, so where did this come from? There's a lot going on here. Where did this minus sign come from? No indication in this, going directly from the far left way over here to the far right, all in one step. No indication of where that minus sign came from. No indication of why. What is it that makes you think you're allowed to use Green's theorem here? From what's written down, circled in green, it's not at all clear why Green's theorem applies. Right? So there's a clarity problem with that. So in order to remove the clarity problem, notice all you got to do is write down these intermediate steps. It's not that much. Take you 10, 15 seconds and much better clarity. Okay, let me pause on that right there. How we doing? Does everybody follow me down to there? Okay. All right, it's almost all over at this point. We need to compute Green's operator, and Green's operator, well, dq dx minus dp dy. So x partial of this, well, I'm taking the x partial, so anything with only has y's in it, it just goes away, no problem. And so just 3. And now minus dp dy, so the y partial of that, just 1. Isn't this nice? It almost seems too good to be true, but the ugliest parts of our vector field disappeared when I took Green's operator. Now that won't always happen, right? I deliberately manufactured this example to be awesome, right? So in reality, it's a toss-up, but if something becomes substantially simpler half the time, that's a big win, right? And so there's a lot of potential for this to be an extremely useful tool when you're needing to compute a line integral. And of course, that's a really easy integral. The integrand's constant. That's a barnyard variety geometric area, so no problem. Okay, how are we doing? Everybody happy with this example? Yep.
Can you explain one more time why you had to switch directions on the orientation?
Yeah, that's right, because I wanted to be able to say that I'm dealing with a boundary, and this curve as given, oriented clockwise, that's not a boundary, because you got to remember, the word boundary is a loaded word. Boundary does not just mean it's where the fence is. Boundary means and oriented according to the convention. This just isn't. Yep.
What would the bounds of the integral be for c raised to the minus?
Oh, for this, if you wanted to compute this brute force, okay, so that the integrand is c minus, so that's this. So in order to do that, you'd have to parameterize c minus, and so it depends on how you parameterize. You'd probably use cosines and sines, and then it'd be 0 to 2 pi if you wanted to do it brute force. Yeah, totally. Everybody else? Yep.
Why did you say we have to parameterize?
Oh no! I'm not. I'm saying you. If you wanted to compute this directly, so her question was, if you wanted to directly compute that line integral. In fact, you wouldn't, and in this case, you really shouldn't, because it's much easier to do this. Yeah. So it was a hypothetical. Alrighty. See another example. weird example. We have 4 line segments given. It makes kind of what I call a triangular figure 8, right? And if I wanted to compute the line integral on this sort of composite curve, minus Green's theorem, this I would have to break it up into 4 separate line integrals. I'd have to parameterize each one of these curves and plug and chug, which I guess I could do, right? But that, 4 separate integrals, 4 separate parameterizations. There's a potential for it to get out of hand, and certainly there's potential for a lot of mistakes, and etc. So, not a desirable solution. Here's the clever move. The clever move is to break up our curve into 2 sort of different curves. Think of it as this green curve plus this blue curve. Now that's all the same line segments altogether, right? But just kind of grouped differently. And you can probably see my motivation. My motivation, for example, for the left part over here is that all of that together is a boundary. It's literally the boundary of this triangle, D1. And I love it when curves end up being boundaries, because I totally love Green's theorem, and this is that's my foot in the door to use Green's theorem, at least on that green part of the curve. Everybody with me so far? Okay, now, what about this blue part of the curve? Is that a boundary? Well, not really, right? I mean, the temptation is to say, it's kind of the boundary of this orange triangle, but not really. No. Boundary is a loaded word. Boundary means oriented according to certain rules, and that blue curve does not pass the rule. It's oriented the wrong way, which is bad. But it's oriented exactly the wrong way in the entire curve. And so all it is, it's just a negatively oriented. It's the opposite orientation on the boundary of D2. The boundary of that orange triangle. How are we doing? Everybody with me? Okay. So, go ahead. Yeah, sorry.
I understand the rules of the boundaries, but what motivated the fact that you traced it in that direction in the first place? Like, what made
because I kind of had to, because I was given literally that these line segments, so for example, it starts at the origin, then it goes to 2, 2, that means it was this. Right? And then when I broke that up into pieces, that means I had to break it up like this. And likewise, this here got broken up into, that and that. And I just found myself, this is what I had. Okay. Yep. Anybody else? Okay, so it's all downhill from here. The curve is the sum of 2 boundaries. Well, okay, it's a boundary plus an opposite oriented boundary. And so with all that in mind, I write this. And then this minus sign gives me that minus sign. And now we're in business. Now we have, you'll notice, literally a boundary line integral, which I can therefore compute with Green's theorem. Here I have literally a boundary line integral. Now, again, there's that whole orientation thing. But remember, I've already dealt with the orientation. The orientation being wrong is why this minus sign is there. But this that remains is literally a boundary line integral, boundary circulation, and so, again, Green's theorem. And then you compute Green's operator. This is just a little bit of algebra, right? You take the appropriate partials of this. dq dx is 5. dp dy is minus 4, and 5 minus negative 4 is 9. Yeah.
So is there a symmetry rule for areas rather than lines, like just lines?
have this as like...
Yeah, I know what you're thinking. So you're looking at this and you're like, oh my God, I love that symmetry, right? So the problem is that I have, I'm not looking at a sum, I'm looking at a difference. That's one problem. Also, until I get down to it being a double integral, until I get down to here, there's definitely no symmetry theorem, because before that, we're talking about vector line integrals, so there is no symmetry theorem that we're going to talk about in this class. Again, technically there is one. It's totally different. It's not worth the trouble. So for vector line integrals, there was no such thing in the first place. And once you've gotten it down to this point, it is far more trouble than it's worth to start talking symmetry than it is to just observe these are really easy integrals. Yeah. And so, and furthermore, to make a symmetry argument, well, again, now you're going to have to write down what your integrand is as a function, and that's awkward because it's different formulas in different parts of it's just not worth the trouble. Yeah. Right. Okay. So Green's operator is 9. This integral is easy because the integrand's constant. This integrand's easy. Integral's easy because the integrand's a constant. These areas happen to be the same, and so the difference is just 0. Everybody good? Okay. All right. Okay, so this next little application of Green's theorem is a how to say this, quirky little trick that you can pull that sometimes is useful. It comes right out of Green's theorem. You can see Green's theorem right here. Notice that I'm applying Green's theorem to this vector field, 0, x. So, all right, I guess we can do that. Not clear why we would want to apply Green's theorem to 0, x, but, I mean, it's legal. And now let me show you why we apply Green's theorem to 0, x. It's because if you compute Green's operator, you get 1. And that's lovely. Having Green's operator be 1 means that we are literally looking at an integral of 1. And an integral of 1 over an area just computes what the area is. So how about that? You connect the dots all together, and what we have is that a vector line integral computes an area. So if you find yourself in a situation where computing the area is hard, and sometimes it is. Sometimes the area is obvious. Sometimes it's a barnyard variety, garden variety shape, in which case you don't need fancy help to compute the area. But if you have a weird, creepy looking area and you just can't, I don't know how to compute the area directly, you have an alternative, which is to compute a vector line integral. Sometimes this is easier. Okay. Now I have an example to show you momentarily. Real quick before you do that, let me talk about this right here. You'll recall this coordinate line integral notation. And I kind of trash talked that coordinate line integral notation last time or the time before, I forget. Most of the time I like the vector line integral notation better. But notice in this case, this one's actually a little more compact. Every so often, it just happens to be that coordinate line integral notation is a little bit more crisp. So you don't have to use that here, but this is the common choice. And so when this fact gets written in math books most of the time, they write it with this notation because it's just that little bit more compact. Yeah.
When you do 0x, is it just like when you put like the integral over the vector field? Is it just like it points like in the same amount of like x direction? So then it just like kind of makes like a transformation that you can find the area of? Is that like how the intuition works? Or?
The intuition for why this works?
Yeah.
To me, the intuition is from the fact that Green's operator just happens to be 1. Now, why Green's operator is equal to 1? I mean, we could draw pictures and go through, and there's different ways to think about it. But I think that's I don't think there's much down that road particularly, so I wouldn't worry much about that. I will point out, by the way, this is by far not the only vector field for which Green's operator is 1. I do think it is the easiest vector field for which Green's operator is 1. Really the big point here is the 1. Yeah. Okay. Now these vector line integrals, coordinate line integrals. Well, you got to parameterize the curve, and these can be a little bit of a pain to compute as well. But there's a wonderfully convenient special case, and I emphasize this works only for this specific coordinate line integral. Exactly and only this coordinate line integral. And furthermore, only if you have a straight line segment as your curve. Look how handy the formula is. This works every time. It's very convenient. Now again, only on straight line segments and only for integral x dy. But nevertheless, really handy little formula here. And notice that the formula says here you're going to look at the average value of x, which is just the average of the ending and starting x coordinates, times the change in y, namely the ending value of y minus the starting value of y. Very compact, and look at that, 4-function arithmetic, right? Really easy arithmetic to compute, and otherwise, a line integral that requires a parameterization and an antiderivative, and could be kind of a pain. Is that anybody? No, okay. So let me put it all together and show you how this can be really useful. Let's look at this example here. Check out my polygon. How would you compute the area of that polygon? And it's a pretty nasty polygon. And now the sort of straightforward approach on this would probably be to subdivide it into a bunch of triangles. And I believe that is 7 triangles, and you could compute individually the areas of all 7 of those triangles, right? And add them up, and that would give you the total area of this, whatever that is, weirdo, kind of a nightmare of a polygon. But here's the problem. Those triangles, most at least of those triangles are not right triangles. What is the formula for an area of a not right triangle? Well, there is one, but it involves square roots, and it's just weird. It's very inconvenient arithmetically, right? Yeah, question.
Can you take determinants of the coordinates as well?
Take determinants of what now?
Of the coordinates.
I'm not sure I don't understand.
I think there's a way of getting the area of the triangle in the plane by taking the determinant of pairs of equivalents or something.
No, I'm just not following.
It's fine.
Yeah, there may be a formula that I'm not. It's been a long time since I took high school geometry, but I don't remember a determinant form. Oh, you're thinking about parallelograms. Yeah. So you could think of the triangles as half of parallelograms. Yeah, you could do that too, but you still have to do that for 7 different triangles, and the arithmetic's still, going to be a lot, right? No, that's a good thought. I like that. Okay, so let me show you this approach, though. I think this is ultimately more efficient. So here's the idea. We want to compute an area. We know an area is a line integral of x dy around the boundary. That boundary consists of 9 pieces, and to compute the total line integral, I can just compute the line integral on each edge. And on each edge, it's a really easy calculation because, for example, if I look on this edge right here, right, on edge number 1 here, let's see here, let's compute the average value of x. The average value of x is the average of 1 and 12, which is 13 halves. Easy arithmetic. The average value, the delta y, how much did y change here? Well, y went from 1 up to 6, which means that delta y is 5. And this is pretty easy to multiply out using this formula. X bar times delta y just gives me 65 halves. And we've computed one of these 9 steps. And just keep going around the edge. Really simple arithmetic. Go all the way through. After you do all the remaining edges. All together, you add these all up, and the answer is 19. So it works out really well. Does that make sense to everybody? Nice little method. Anyway, it's just one application of Green's theorem. Okay, why am I erasing that? There's no need to erase it. Okay, so let's talk about flux now. Flux through a curve. This is a very similar idea to something we've talked about before. We've previously talked about flux through a surface, right? Flux through a surface was a way of keeping track of how much quantity of fluid per unit time is flowing through a surface. Well, here I'm going to argue that a morally equivalent situation is if I'm in 2 dimensions and keeping track of how much fluid is flowing through a line segment instead of a little flat piece of surface. So this is just kind of the 2-dimensional version of the idea we talked about in Chapter 3 of flux. And we get the analogous answer. That flux is F dot N and then times the size of whatever it is that you want to keep in track, that you want to know how much the fluid is flowing through. So this is, like I say, highly analogous to the Chapter 3 result. If you are interested in a challenging exercise, go back to Chapter 3, look at where we motivated the definition of flux. It was in a little computation. And adapt that computation to this circumstance. This is not a sort of a generalization to a higher dimension. This is a reduction of a 3-dimensional calculation we've seen down to a 2-dimensional example, sort of 2-dimensional equivalent. So, but it's a nice little challenge exercise. If you get stuck, of course, you can come to office hours. I'll be happy to walk you through it. The punchline is, this is what we call flux, and it computes the rate of flow of fluid through the line. Okay. So, let's see here. Let's consider now a related idea, boundary flux. It means exactly what you think. It means flux. Flux is flow rate. By boundary, we mean, and again, this word boundary is a loaded term. Boundary means oriented, furthermore oriented according to conventions. And the convention is arbitrary, and 150 years ago they could have chosen a different choice, but they didn't, and convention is what it is. Planet Earth does it a certain way. So we're going to get on board as usual. The convention here is that boundary means outward, away from where the area is. Okay, so boundary flux just means outward flow rate across the boundary. Okay. So, how to compute that? Now, we're not going to get through this right now, but I'm going to make a quick geometry argument that will pay off in a minute. I'm eventually going to find myself looking at a dot product of a vector field and our normal vector. I'll be looking at this dot product in just a minute. I'm going to make the innocent observation here that dot product depends on the magnitudes of those vectors and the angle between them, none of which is affected by rotating 90 degrees. If you rotate both of those vectors 90 degrees, the results have the same magnitude, the results have the same angle between them. And so that dot product is the same as this dot product. And you can check for yourself, easy little geometry to think about, that if you have an outward oriented normal vector, keep in mind that's the convention, that's the definition of boundary orientation. If you have an outward oriented normal vector, the counterclockwise 90 degree rotation will give you a tangent vector, but furthermore, a tangent vector for which the solid is on your left. And so the properly oriented normal rotates into the properly oriented tangent. So N rotates into T. Everybody see that from the picture? All right. Okay. So with that established, if I want to compute the grand total flux over the entire curve from the previous page, flux is F dot n times length. If I'm looking at a little short little piece of curve there of length ds, that length is ds. And here's the big payoff. These being equal means those are equal. And what's awesome about this, we'll finish this next time, but what's awesome about this is that this integral that I don't know how to compute, namely an integral blah 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 in ds, we've never seen that before, we don't know what to do with that, turns into blah 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 TDS, which is dx, which I do know how to deal with. And so computing this boundary flux effectively turns into this vector line integral. We'll pick up there on Monday. So see y'all on Monday. Have a great weekend. See you later.